have to learn Kirchhoff's laws this week if you don't already know them. Combine that with Ohm's law that you covered on Thursday with John, and you have everything you need. Everything you need to analyse circuits with dependent and independent sources. You talked about those on Thursday, and with resistors. So for that whole family of circuits with just those elements, Ohm's law, Kirchhoff's current law, and Kirchhoff's voltage law give you everything you need. In terms of the fundamentals, that is it. And you'll have Kirchhoff's current law at the end of today. So we've talked about charge. We've talked about current being the flow of charge, voltage and power. You have covered voltage sources and current sources, both dependent and independent, and you've talked about, we've done resistors and Ohm's law, power calculations of simple circuits, and you even used Teligens's theorem to solve for some unknowns in simple circuits. Conservation of energy, the power absorbed by every element in the circuit must sum to zero, or the sum of the powers absorbed must be zero. And there, just as a reminder, is Ohm's law for you. All right? Remember this. There's voltage trying to push the current through the circuit, but the resistance is opposing the flow of current. What if we have more complicated circuits with multiple unknowns? Well, we're going to use Kirchhoff's laws. Okay. We apply Kirchhoff's current law at nodes, Kirchhoff's voltage law around loops, so we need to know what nodes and loops are. And we'll also cover that today. The first thing to note is we're going to use what's called a lumped parameter model, or a lumped circuit model. And it's this, that the interconnects or wires are really irrelevant in terms of the circuit. They connect things up, but they have zero resistance. So when you're doing circuit analysis, you kind of can ignore the wires or the interconnects. The voltage at any point on a wire between things is going to be the same. So what this means is there's no resistance in this wire. So the voltage at any point there is exactly the same. And the same for this other node down the bottom here. The voltage at all points on that is exactly the same. No resistance. Voltage is everywhere the same. They won't really play a role in circuit analysis other than telling us how the different components are hooked up. So these interconnects between elements are called nodes. The interconnects between elements are nodes. This, the whole thing up the top there, I could call node 1, and this thing down the bottom there could be node 2. So the piece of wire with nothing between it, that's all a node. This is an approximation. Wires do have resistance, or interconnects do have some resistance. But this approximation of all the action happening in the elements, in the battery and in the resistor only, what are we assuming? We're assuming things like the speed of propagation of a signal around the circuit is insignificant. So if I close a switch, connect a battery up, instantaneously, effectively, everything is just set up. All right, that's sort of what we're assuming. This breaks down under certain condition, and it breaks down when the circuit dimensions are of the same order as the circuit's operating wavelength. So you might start, this might start breaking down if we went to different transmission lines in power systems or something. If we wanted to analyse those, this type of assumption might break down because we might have very big circuits, for example, or so that sort of thing. There's also a lumped element model in mechanical systems. If you've done some mechanics or you're doing it, where you assume that all objects are rigid bodies and that all interactions between the bodies take place at joints, springs and dampers. But kind of like within the rigid bodies themselves, nothing happens. So there's a lumped model in mechanical systems. This is the lumped model in electrical systems. Essentially saying the wires don't really play a part. It sometimes breaks down, but for you, that's all you need to worry about. How many nodes are there here? How many nodes are there in the circuit? 8. 2. A couple of 2s over there and an 8. So there are big differences. What I say is you should only really be in... you shouldn't have 2 nodes separated only by wire, only by interconnect, because the interconnect isn't anything of significance. So I can see you might have said 8 because you called this a node and this a node and this a node and maybe even that and that and that and that and that. But the reality is this whole thing up the top there is all just connected to each other by wire. It would all be at exactly the same voltage, and therefore that whole thing is just one node, and this whole thing down here is just another node, node 2. So really there are only just 2 nodes in that circuit. So if you've got 2 points, they're connected only by wire, you can consider them to be part of the same node. They must be at the same voltage. Okay? So I'm glad somebody said 8 because it really highlighted the point. How many nodes are there here then? 4. Okay, let's have a look. If I call that top one 1, that's sort of covering all this business. Here's a node 2, that's sort of all this stuff. But I could still have one here between those resistors, and there's another one here between those resistors. So all those 4 points could be at a different voltage level. Points 1 and 4 or 1 and 2, they're not connected only by interconnect, so they are indeed separate nodes. Are there any questions about this definition of nodes? In a minute we'll apply Kirchhoff's current law at nodes, so that's why we needed to know what a node is. All right, in that case, get on to melts, and you can tell me, don't tell me where they are, just tell me how many nodes. And the question should be open on melts. So you can take 30 seconds, chat to your neighbour. You don't have to do it yourself. If you're confused, feel free to confirm. Make noise. Hopefully melts has the correct answer as one of the options. I've got 40 responses. Keep them coming. Earn those participation marks. I think you should get triple points at least for coming in at 8 o'clock when everyone else has got a public holiday. Were you able to get in last week? Not last week either? Okay. We did an update of the student list last week, but did you register late? On Monday? Okay. So we'll try again. We'll do another student update list later. All right, let's have a look. For those who have... All right, we've got 108. That's pretty good. And we've got 120. This is flying. All right, can I lock it now? All right, I'll lock that there. So 93 out of 122 people said there are 3 nodes there. Some 20 said 6. So I'll see if I can work out where 6 comes from. The correct answer is 3. The 3 nodes are, there's one up the top, and that includes anything that's connected to that point only by wire. So it includes all of that. That is one node. It is not 3 different nodes or 4. That's one node. There's 2 down the bottom here. You know, all of that, that's 2. So really, there's only this one as a third one. The only other thing that can be different. Now, if anyone who had 6 and thought it was 6, and it's not clear now, you can whack your hand up. You get a coffee for asking a question. Free coffee voucher for asking a question, not answering one. So is that, for everyone who put 3, I assume that's what you did, but if you put 6 and you don't get it still, you don't want to ask now and get it. Oh, yes?
Are there any circumstances in which that voltage can be different on the same bit of wire? Not really.
Well, not when we're making an idealised model. Yeah. Actually, absolutely it is. Yeah. Because a real wire will have some resistance. The question is, if that resistance and the bulb are 10 ohms, 20 ohms, 1,000 ohms, and it's, 0.1 ohms per metre, then it's pretty insignificant. So yes, it's an idealisation, but just to show I wasn't like, there you go, free coffee voucher for asking a question. There you go, excellent. That's what we like to see. Any other questions? I'm very well, thank you, but that doesn't get a coffee voucher. I'm awake to that. All right, I do need a demonstration though. I need at least 4 students, and I do have coffee vouchers. 4. Oh, again? Oh man, I'm going to be responsible for your caffeine addiction. Come down, please. I need just 4. 4. Yeah, just come down. First 4 down. We're going to see. We're going to get these same boys again up the back. All right. I need one more, I think. Okay, see, what we're going to do is I need 2 of you starting here, facing that way. Over here a bit, over here, and in a line. So your current in a wire going that way. Yeah. No, you're over here. No, you're not resistance. Don't get your hopes up. Come here, and you're in a wire. You're going this way. You're both. So your currents, and you're flowing. I'm a node, and you're flowing into me. So both come in. There's current coming in. Here, go through me. Current going out. Look at that. What did we notice there? How many students did we start with? How many did we finish with? 4. I have no idea what that means, but thank you very much. I know why you're waiting. Jeez. They can't get away with any. Oh, there are only 3. Oh. No, I'll get another one. Thank you very much. Conservation of students. We've just demonstrated the law of conservation of students. And that is what Kirchhoff's current law tells us. If I'm at a node, I have the sum of the currents entering that node, I was the node, remember, is 0. The sum of the currents entering the node is 0. If that wasn't the case, charge would either be building up at that node or getting depleted from that node. That's not going to happen. It can't happen. Where would those students have gone? The ether. They may have just vamooshed or... Yes, question?
Here you have a node as a point, but earlier you had nodes as wires.
Yeah, so I could always collapse a wire into a point without any difference. So when we apply it, it's an excellent point, and you're going to get a coffee. In fact, you might even get 2 for that. No, only 1. Because you might. There you go. So yes, I've drawn it as a point there, but when we apply it in a few slides' time, we will apply it to that more general notion of a node. Keep in mind, you could always collapse anything that's by interconnect. You could collapse it all together into a single point. So that's the way we're going to be seeing it. So the sum of the currents entering any node is 0. And hopefully it doesn't take too much imagination to think that makes sense. If I was constantly going to have that not true, there'd just be all this charge building up at that point. That's not going to happen. I1 plus I2 plus I3 equals 0. Now, you could also say the sum of the currents exiting a node is 0. It doesn't make any difference. You could also say the sum of the currents entering is equal to the sum of the currents exiting. All of those things are equivalent statements. Okay? Sum of the currents entering 0, the sum of the currents exiting 0. But when you're analysing any particular node, you need to know which way you're going to do it. Analyse node A, I'm going to say the sum of the currents entering this node is 0. Write down what that means. Write down the equation in terms of the currents coming in. You could actually then jump to another node in a different part of the circuit and say, oh, the sum of the currents exiting this node is 0. That's fine. I think there it says something about you have to be consistent, choose a reference direction and stick with it for the whole circuit. Rubbish! You don't need to do that. Node by node, you can make your own decision. This node, I'm going to say the sum of the currents entering. This node here, it's going to be the sum of the currents exiting. Just don't confuse yourself. So most people, you probably adopt one way of doing it and stick with it. But it really doesn't matter. In this case, again, I1 plus I2 plus I3 equals 0. Keep in mind, we say there's a current I1 flowing in that direction, but I could get that to be minus 6 amps. Can't I? I mean, you don't have to guess which way current's flowing in a circuit. You've got an arrow and you've got a plus or minus sign. So you might say I1's that direction. You might get a plus or minus. It doesn't mean you have to know which way the current's flowing before you do this. So a historical vignette. Gustav Robert Kirchhoff, 12th of March, 1824 to 1887, was a German physicist who contributed to the fundamental understanding of electrical circuits, spectroscopy, and the emission of blackbody radiation. He coined the term blackbody radiation in 1862, and 2 sets of independent concepts in circuit theory and thermal emission are named Kirchhoff's laws after him, as well as a law of thermochemistry. Many different ways of saying Kirchhoff. How would you say it? Kirchhoff. Okay, very good. Kirchhoff. How would you say it? Kirchhoff. Yeah, that's right. How would you say it? Kirchhoff. That's good, I like it. How would you say it? Kirchhoff. What about Kirchhoff? Kirchhoff? There are so many different ways of saying it. I find it very confusing. His middle name's Robert, so we're going to call them Bob's laws. All right? It's just a lot easier, gets me into far less trouble, gets my tongue far less tied up. So, Bob's laws. Bob's current law and Bob's voltage law. So, the question here, we applied it just at a point there. Now we're going to apply it to this. It's exactly the same thing. Given the network, find IT. What must IT be? Some of you will yell that out, but let's do it systematically. Let's say at this top node here, and just to be clear what we're doing, I'm going to do that. That's our node. And I'm going to say the sum of the currents entering the node is 0. Sum of currents entering that node is 0. IT is entering. So I get IT. Then I go plus, I'll map it out really fully, plus this current here. What's that?
So we have to take it negative or?
Yeah, well, what's that current there, that up arrow into that node? Negative 10. Plus minus 10 milliamps. Plus negative 40. Plus negative 20 equals 0. Absolutely, this plus this plus this plus this, you wouldn't normally bother maybe expanding it out that fully. you can see what we're going to get. IT is 40 plus 20 plus 10, which equals 70 milliamps. Any questions about how we've applied that? You could have done it at the bottom node. You could have said the sum of the currents exiting is 0. And you would always get IT as 70 milliamps if you've done it correctly. I had to edit that slightly. All right, so you're going to do this one. And I will now open it on melts. Okay, so that question should now be asked on melts. You just have to do one Kirchhoff's current law at the top or bottom node here. There are only 2 nodes again. Just have to apply Kirchhoff's current law. The only slight complication, not really one, there is a dependent current source over here, but that's okay. Just write down the sum of the currents entering the top node is 0, and you'll get an equation, and you can solve for IX, the mystery current. So see how you go. You can have chat, take 30 seconds, 40 seconds, even a minute. "30 responses, good. "70 responses, nearly all correct. "100 responses. Nearly everyone says that IX is 2 milliamps, so I probably don't need to go over it, but let's just double check. So let's suppose I'm interested in that node. I sum the currents entering that node to 0, so I must get IX plus 10 minus 5IX minus 2 equals 0. Therefore, minus 4IX plus 8 equals 0. Therefore, IX equals 2 milliamps. And we're done. And 128 people have now answered. All very good. Here's another one. Apply KCL at every node here. Someone, can you give me a number between 1 and 5? 3. Okay, let's do it at 3. Node 3 in the middle here. This one here. Let's say the sum of the currents exiting is 0, just for fun. So I need to work out what that one is. What is it? Negative I2. And now I need to add this one, which is what? I4. Then I need to add that one, plus I7. And I need to add that one, which is negative I5. So that must equal 0. I think you're getting the idea. You could now apply that at all 5 nodes, and you've done everything you can with Kirchhoff's current law for that circuit.
Jim?
Yes?
Yeah, instead of we can write positive I2 and negative I4 as well. If we change the sign.
You can change all of those signs if you want. Yes, you could have had plus I2, minus I4, minus I7, plus I5 equals 0. You get that just by multiplying both sides of this equation by minus 1. And clearly that's the same equation. Yep. For good clarification. I need a volunteer to come up and solve this one for a coffee voucher. Would you like to come up? Yep, excellent. You grab the pen here. Ready to go? Very fancy. You ready? I want you to apply KCL to this circuit, please.
Oh, yes.
No, you can sit down. That's all right. Thank you very much. Come and get your coffee voucher afterwards. Yep. All right. That's it for Kirchhoff's current law, actually. That's all you need to know. Sum of the currents entering in node 0. Kirchhoff's voltage law now, rather than summing currents at a node, is going to be something to do with summing voltages to 0. And these are voltages around a loop. So we need to know what a loop is. Well, a loop is any closed path through a circuit in which no node is encountered more than once. And a closed path means the path starts and ends at the same node. So you start at node 1, you might go through 2, 3, 4, 6, 9, 12, and then back to 1. That's your loop. But I didn't go through any node twice along the way other than the one I started and finished with. That's what we mean by a loop. And a branch, by the way, is a portion of a circuit with a single element and the nodes at each end. So it's the stuff that's not a wire. So this is a branch between those top. So here, this would be node 1 and node 2. Here's a branch, there's a branch, and there's a branch. Effectively 3 elements, 3 components, 3 branches in this circuit. A loop would be starting at node 1, going down to node 2, and coming back to node 1. Or it might be doing it this way, in that smaller area. Both of those are just loops from 1 to node 2 and back to node 1. So they meet the requirements of being a loop. And even in that simple circuit, there are in fact 3 loops. If you like, I could loop around that, I could loop around that, or loop around the whole thing. So they're nodes, they're loops. We'll do more on loops in a minute. Well, that's a loop, clearly. Don't try that at home. I want to know how many branches this circuit has. This is branches, not loops. And I'll give you another melts on that. And unlock it. There we go. So how many branches? Effectively saying how many things on there that aren't pieces of wire, that aren't interconnect. It's really all that a branch is, an element. There's one. Okay, 100 people, nearly everyone's saying 6. There's 1, there's 2, there's 3, there's 4, there's 5, there's 6. So they're the 6 branches, elements, components in this particular circuit. Where are the loops? Well, there are lots of loops. Remember, provided I could identify all the nodes. One, how many did we say there are? 2, 3. It's that one we did before, just with 3 nodes. But here's a loop. There's a loop. Okay, that meets the requirements. I'm going from 1 to 2 back to 1. Here's a loop. Here's a loop. Here's a loop. They're all valid loops, which is great. We'll traverse in a certain direction, so I'll just put an arrow on those. Where are some more loops? Okay, what about this one? Yep, there's one. What about some more? Okay, what about this one? There's one. There's one. So all of those things will be loops. I'm not going through any node twice along the way. I start and finish at the same place. So what's not a node? Does anyone think they can come up and show me something that's not a node? More importantly? Oh, sorry, what's not a loop? Yep. Do you want? Oh yeah, okay, if you can. Very good, very good. Better get your coffee voucher. You missed out, didn't you? Sorry, not you. Okay. Next time. Thank you. Okay, grab the pen. Here it is. It's the magic pen. What's your name again? Sorry.
Marcus.
Marcus will show us not a loop. Okay, now I'm going to vote on this. Who thinks Marcus has shown us something that is not a loop? Who thinks Marcus has shown us something that is a loop? It's interesting. That's a good one. So why is that not a loop?
Because it passes through the same node twice.
Which node does it pass through twice?
Number 3. It passes out of the light bulb just underneath between the resistor.
See this here?
And
At
then it
first,
passes again.
okay, look at that. If this node was node 2, and this is node 1, and this is node 3, it went from 1 up here to 2 to 3, and then back to 2. So here, and then back to it. So it's passed the same node through the same node twice, but it doesn't look like it, so you have got to be careful. Brilliant example. Thank you very much. Oh, coffee voucher. Sorry, mate. There you go. Well done. That's a great example. Just got to be a little bit careful. Just because you draw something that starts and ends in the same spot doesn't make it a loop. Really see if you can get that one. You visited this node twice. Node 2 was visited twice as you looped around. Another one that's not would be this. Just starting here and stopping there. I didn't go back to the same node. So that's not a loop as well. So they're the two good examples of what you have as not loops. In the next lecture, we're going to some voltage drops around a loop. That must be 0. That's Kirchhoff's voltage law. Then you will be all powerful. I'll leave you with the famous last words of Oscar Wilde. Either that wallpaper goes or I do. See you on whenever the next lecture is. Wednesday.